respiration. This is also the chapter that you're going to write your your practical on in the exam. Okay? So you want to pay attention. And then also, quickly want to say, what do you write on for the exam? Your question paper is going to be 3 hours, not 2 hours, 3 hours, 150 marks. Then you write on quantitative aspects of chemical change, mole tables, mole calculations, that chapter. Then also energy change, that is that endo and exothermic graphs. Then types of reactions, this is that acid-base reactions as well as the redox reactions, that gaan nou be obvious. And then the gases, this chapter that we are on now. Yes.
Juffrou, wat is alles?
Right, and then if you look on your ATPs, these things that I've handed out to you, and you read through them at the beginning of the year. And you read through them, and you go to term 4, you'll see that in term 4 they speak about acids and bases and redox reactions, but we've already done that. So you're going to write on that this term already. So don't think, oh, this is part of term 4, so I don't write on it. You do write on it because we've already done it. Now, why do I do this? Why do I give you more work to study? 2 reasons. Reason number 1 is then you study for it now in September and you study for it end of the year. So then you'll do better end of the year because you've studied it twice. Okay. Second reason that I've completed this work is I want to revise your whole year's work, especially the work that I was not here for. Okay, that intermolecular forces and the tetrahedral, and that I want to revise thoroughly next term. Okay, so that is why I've completed all of the work now, and so you write on all of that now. Yes. Next? What? You write on it next year. You're not going to do it next year in class now.
By next year, we're going to be done with the chapters and just revise it.
Yes.
So this is the last chapter.
Yes. Yes.
Okay.
Last chapter of the year. Okay. Right. So, acids and bases. First of all, we are going to look at matter. Matter consists of particles that has mass and volume. So everything has mass and volume. And they move continuously. They are constantly moving. And in grade 8, you looked at when it is a solid, it vibrates on the spot. When it's a liquid, it glides over each other. When it's a gas, it's all over the place. Then intermolecular forces play a strong role in determining the melting and the boiling points of substances. And you had a whole chapter on that. Because you saw the stronger the intermolecular forces, the more energy it will take to overcome those forces. You spoke about London forces, dipole forces, and hydrogen bonding. You remember that? Yes. Right. Now, this chapter is called gases. So we want to look at gases. We do not want to look where it has condensed and formed liquids or frozen and became solids. We only want to look at gases. Now, when gases are at high pressures and low temperatures, what will happen to them, Seba? Michelle? When you're at high pressures or low temperatures, what happens with gases? With gases. The thing in your head, when it becomes very, very, very cold, what happens with the gas? Yes? See ya? It condenses or it forms a solid. Okay, so we do not want it to condense. We do not want it to form a solid. We want to work with gases. So when we have very low temperatures or very high pressures, it condenses. So then it's not a gas anymore. So we want to work with the opposites. We want to work with low pressures and high temperatures. Okay, so I say here, with gases, the intermolecular forces that cause it to change phase has an effect at high pressures and low temperatures when the particles are close together. Zara, let's pretend like I have a big container with gas. When will I have a high pressure? When I hold it like this or when I squeeze it together like this? When you squeeze it together, when you make the volume smaller, the particles are closer together. Right, so on that note, Sorry, I'm going to go to here. So here, this one. Here you can see I have particles that are vibrating on the spot. You can see there, we measure the temperature in Kelvin. Okay, we're going to get to that in a moment. Measure the temperature in Kelvin. And then when I heat it up, what's going to happen to the particles? They're going to move faster. You can see the kinetic energy, the movement energy becomes more. They glide over each other, and then after a while they start to move very fast all over the place. Okay, so I just want to get to a point. Okay, now that we are here, can you see there the temperature remains constant? Okay, but let's follow one particle. Let's follow this particle. There you can move it slowly, then faster, slow. But faster, fast, slow, fast, slow, fast. Do you see that? So it goes faster, slow. Why does that happen? Because there's collisions the whole time. When it collides, it transfers energy to another particle. But overall, all the particles together have an average kinetic energy. And that average kinetic energy is linked to the average temperature. Okay, so an individual particle might have low energy and then high energy, but all together they have an average energy. Just like in this class, I can, let's say at second break, I ask the teachers, I have 11 D after break. How are they today? Are they a bit lively? What's their mood? Then they can say 11 Ds are very reserved today. Do they speak about, or do they mean every single one of you are relaxed and in your place? No. There's some people that will always have a higher energy, right? But they spoke about the average energy of the class. Okay, so the same thing. If I have gases in here, okay, then if I hold it like this, and hold it against my body, I'm actually heating up. Yes? Oh, really? Rory?
He or she could be late.
He or she? Right. So when I hold it like this, okay, I heat up the particles close to be inside the container. So these gas particles heat up, but the gas particles that are further away, they are a bit colder, so they move slower. Right? Or if I exhale in here.
But you're letting the gas out.
Woo! I am letting the gas out. Someone didn't wash this. But if I exhale in here, my body is an exothermic reaction. I exhale warm gas particles in here. Right? Then the average temperature or the average kinetic energy of these particles will change. Okay. So that is linked with the next one. The kinetic molecular theory. Kinetic means moving. Molecular, molecules. Theory. The kinetic molecular theory determines the following. They say that all gas particles consist of mass and volume, and because the particles are far apart, they can be compressed. Okay, so back to here. If I look at this one here, and I pump in gas in here. Okay, we can see there the gas particles, they will fill the whole container. Okay, it will start to collide, then the pressure will increase inside the container. And because there's gaps, spaces between the particles, I can actually compress the particles together, and I can take them further away from each other. So because there's spaces, I can compress the particles. I think somewhere here the lid will pop. Like that. Okay, right. Then if the particles are far apart, then they exert no force on each other. If they're far apart, there's no attraction. It's almost like a long distance relationship. Then there's no attraction force, except when they collide. When they accidentally come towards each other, push, they collide and they're gone. Then All the particles are in a continual, hello Rory, in a continual state of motion and therefore have EK. Zara, what does EK stand for again? What energy? Kinetic energy. They have kinetic energy, that is movement energy. Okay, and they will move randomly and they will fill the container. Move randomly, they don't have a specific road they will move wherever they want to go. And fill the container, that happens due to diffusion. Tony, where in your everyday life do you experience diffusion? If you don't, you need to go see a doctor.
If you in school, when you use focus,
No.
use from there.
No, but good guess. Tsepo? Were you? And then what happens? And then what happens? To the people around you.
When you go to the toilet, when you let everything out, then you feel relieved. You've diffused the situation.
Yes, that's a good one, yes? No, I just handed out all of my extra ones. Sorry. Okay, so diffusion is when something goes from a higher concentration to a lower concentration. So, for example, when I fart in front here, the gas will slowly diffuse to a lower concentration to you. Or when you burp, high concentration, and then the smelly gas goes to the people around you. Or when you have cool drink and or water and you throw in like cool drink or also whatever, and then it diffuses down where it goes from a high concentration to a lower concentration. Say again? Or a pill, okay. Or we can mention all the 100 things in life. Yes. Okay. Then the next thing there is the collisions when they collide are elastic. Elastic means that no energy is lost. So there's a transfer of energy. Okay. Now, in this chapter that has to do with gases, we're going to work at STP. And we're going to work with absolute temperatures or absolute Kelvin. Okay, first of all, what does STP stand for again? STP stands for standard temperature and pressure. And you should know that is 0 degrees Celsius and 101.3 kilopascal. That kilopascal is the same as 1 atmosphere. We say it's 1 atmosphere. Okay. So at STP, at these conditions, if you have 1 mole of gas, okay, 1 mole is 6,02 times 10 to the power 23 particles. If you have 1 mole of gas, it's going to take up this space. This is 20 liters. So 22 is like if you take another layer here and you just add it. That's about the volume that 1 mole of particles take up at STP. That is like quite small for 6,02 times 10 to the power 23 particles. Remember last year when I explained more, I said if you have so much, the day when you were born, someone gave you so much 1 rand, and you spent 1 million 1 rands per second, till the day that you die at the age of 99, at the age of 100, you will still have 99% of your money left. That is a massive number. Massive number. Okay, it's unthinkable, the number. That's how many particles are in here at STP. Okay, that is like, that must explain to you just how small gas particles really, really are. Okay, now, here I said, so 1 mole takes up 22.4 deciliters cubed or liter. Then I've spoken about now Kelvin. Kelvin. So yeah, in America, what unit do they use to measure temperature? Degrees Fahrenheit. In South Africa, we use degrees Celsius. So universally, the scientists came up with a new scale, and it's called the Kelvin scale. Okay? And how do these two things link? When you have any degree Celsius, so like 180 degrees Celsius, and you add 273 to it, you get the temperature in Kelvin. Okay, now this formula to go from Kelvin to degrees Celsius, that is not on your data sheet. Okay, so you have to go memorize it. Okay, this capital T is for Kelvin and the lowercase t is degrees Celsius. Right, now we have 3 temperatures that you should know. The first one is absolute zero. That is like the coldest temperature that they have ever found to exist. Okay? Absolute zero. The coldest known temperature, that is negative 273 degrees Celsius. That is very cold. This morning I think we went to negative 4 at some places when you are close to the water. Okay? And that was very cold this morning. So minus 273 is very, very cold, and that is 0 Kelvin. You don't get smaller than 0 Kelvin. Then the triple point of water is a temperature where all 3 phases exist. So where you get solids and liquids and gases. So that magical temperature where you can exhale and there's water particles and you can drink water and you have ice and all 3 will be like in equilibrium with one another. That is 0 degrees Celsius or 273 Kelvin, and then the boiling point of water we all know is 100 degrees Celsius. Okay, now I've said this formula is not on your data sheet, but what you do have on your data sheet is in the info table there. You can see it says standard temperature 273 Kelvin. Okay, because that is 0 degrees Celsius. Okay, so that is on there, but the formula how to get from the one to the other is not on there, but at least that number will maybe help you get to it. Okay, cheese. That is going on to YouTube. Okay, then pressure. What? What? It's going on YouTube. I'm recording the lesson for the people that are not here. Okay, who did not sign their Popia? Really? Yeah. He's not in the video, so it's fine. Okay. Right. So pressure is when things collide, when they exert a force on one another. So that is either in newtons per meter squared or in Pascal. So we use Pascal to measure pressure. Pascal. Okay, so you need to be able to convert the volume part because we're busy with working with gases. But you have done that, yes. And you need to transfer from Pascal to kilopascal and kilopascal back to Pascal. Okay, just quickly, centimeters cubed, Rory, is the same as what? I'm going to give you a choice. Is it milliliters or liters? Milliliters. Decimeters cubed is liters and meters cubed is kiloliters. Who has a JoJo tank at home? How big is your JoJo tank? No, it won't be 100, 2,000. Maybe 2,500? Liters is how many kiloliters? 2.5. You divide by 1,000. 2.5 kilos. Okay. Then the last bit of thing for today is temperature and kinetic energy. Now I've said this now, but we're gonna just highlight now as well. The temperature of a gas is a measure of its average kinetic energy. So from now on until the day you walk out of the school, when you've collected your matric certificate in January of 2026.
What?
Your matric certificate. Then from today until that day, when you hear temperature, you must tell me kinetic energy. Or when you hear kinetic energy, you must think of temperature. Those two things go together. Okay? So when we heat a gas, when we make it warmer, then the gas molecules absorb the heat energy, and then their average kinetic energy will increase. So they will move faster because they gain the energy and they will move faster. So the temperature of a gas is directly proportional to the average kinetic energy. Now, a few things that you need to know from there. At 0 Kelvin, at that coldest known temperature, the particles have no kinetic energy. So they're not even vibrating on the spot. They are basically standing still. And then there will be no pressure. Because they won't collide against each other or bump or anything like that. There's no pressure. And then inside a container, the particles move at different speeds. Okay, that is what I showed to you on that simulation. They have different speeds. And when they collide, the speed of a particular particle may change because it collides and it was going slow and it collides and now it's going fast. But altogether, the average speed of all particles will remain the same. So thus the temperature will remain the same. Okay, so now, I know you asked about your allo task. Okay, I'm going to give you your homework. It's your choice which one you want to do now. Your homework is going to be here on page 6, question 1, 2, and 3. And you can do it on the paper, on the page. You must convert back and forth and back and forth and back and forth. Okay, so question 1, 2, and 3. Or what?